tonight I'm going to concentrate on Volcanoes and Society and show you some examples, largely drawn from my own experience, of the effects that volcanoes have on society and how you manage the risks and hazards that are associated with volcanic eruptions. Firstly, just give you just a few facts and figures about volcanoes on the Earth. There's 551 historically active volcanoes. They're actually about estimated at least 1,500 active volcanoes around the world, and you'll see that the 551 is about a third of those. In fact, most volcanoes, of course, they have long periods of dormancy. About 1,000 of them don't have any historic records at all, so it's quite common for volcanoes with no historic record to start erupting, and that was Mount Sinabung in 2010. There's about 50 eruptions somewhere on the Earth every year, and we don't hear about many of them. We hear about Krakatoa, of course, over Christmas, but the reason we don't hear about them is that they're either in very remote islands or they're in places with very low populations, and they don't really affect anybody very much, and so the media doesn't really pay much attention to them. Over the course of history, there's records of about 250,000 fatalities from volcanic eruptions, but probably the real casualty figures are rather high. The records aren't that good. The economic and social costs are high, as I'll show you later in this lecture. And also there are large eruption effects on global climate. I'm not going to talk that much about that topic tonight. So although volcanoes, there's no increase in volcanism on Earth, roughly that 50 eruptions per year is still been the case for tens, if not hundreds of years. But the reason that volcanic risk is going up is because of global vulnerabilities increasing. Populations are growing, building up towns around volcanoes. There's increased infrastructure, increased interdependency, and I'll show you the effect of the eruption in Iceland in the UK later in the lecture. Where are most of the volcanoes? Well, you can see those 1,500 volcanoes are on a map here of the Earth, and you'll see that they're very strongly clustered around the tectonic plates of the Earth, places like Japan, the Philippines, Indonesia, South America. So they're mostly at places where either the tectonic plates of the Earth are splitting apart, or in fact most of the world's dangerous volcanoes are where the tectonic plates are actually colliding, and that's what's happening in somewhere like Japan. Okay, the main problem with volcanoes from a hazard point of view and risk point of view is that there's not just one kind of hazard. There's several kinds of hazards, and this gives you 6 examples. There are actually other ones. There's something called a pyroclastic flow, which is essentially a hot avalanche of dust and rock that goes down the volcano, and I'll show you some films about that in a moment. There's volcanic ash itself, which can go up into the sky and stop, for example, commercial airlines or military aircraft as well. And volcanic ash can cause health hazards. There's tsunamis, and of course that was very much highlighted by Krakatoa, where a bit of the volcano, because of its activity, fell into the ocean and caused a tsunami. That's the famous Hosogai print of a tsunami in Mount Fuji. And then on the bottom left, there are things called lahars. Again, I'll show you some films to show you what a lahar is, but basically it's a flood of mud and rock that's very commonly happens in association with volcanic eruptions. And then there's explosions, violent explosions if you're near the crater, and volcanic gases, noxious gases can come and can cause health difficulties or even death. And then there are lava flows which can burn, usually don't cause casualties, but of course they can cause an awful lot of destruction by burying and burning. So just give you some examples of these, something called a pyroclastic flow. And this is really, in some ways, if we go back to Mont Pelée, the volcano on the island of Martinique in the Caribbean in 1902, there was a very large pyroclastic flow which destroyed the city of Saint-Pierre on the island. And it was really almost the birth of modern volcanology, because it was such a dramatic event that the story went round the world, and 29,000, virtually everybody in the town was killed by the pyroclastic flow. And you can see in the bottom right-hand side the destruction. It was almost like a sort of nuclear explosion, almost devastating the town. And then I've just highlighted that 29,000 people die when political priorities take precedent over public concerns. And it's just to make the point that it's often not the natural hazards which cause the death, it's the poor response to that natural hazard for whatever reason that turns an event into a catastrophe or a disaster. In the case of Montpellier and Saint-Pierre, the volcano had actually been active for a few weeks before the main event. And there were some elections coming up, and there were some engineers and doctors who knew enough about science to really ask the politicians in the town and the mayor that they should really think of moving people out of the town. But there was an election on May the 10th, 1902, and the politicians were very reluctant to put a halt on the election. And on May the 8th, the pyroclastic flow came out. They delayed their decision, and that's really a significant factor in the tragedy. Okay, I'm going to show you now a film about pyroclastic flows and the hazard, just to give you an idea of how dangerous these things called pyroclastic flows are.
One of the most deadly of volcanic hazards. They are rapidly moving avalanches of hot rock, dust and gas that flow down the sides of a volcano and into surrounding valleys. They can climb up and over ridges and high ground. They are dangerous because they flow much faster than a person can run, and often faster than a car. So for those in their path, there's little chance of escape. What makes them especially lethal and devastating is that they're extremely hot. During the day they appear grey and ashy, but at night they can be seen glowing red hot. They destroy and burn anything in their way. Death or severe injury is certain for those caught by a pyroclastic flow. There are two main ways pyroclastic flows may form. Sometimes a volcano explodes and forms a fountain of hot pulverised rock and gas that first rapidly rises into the sky and then falls back, forming pyroclastic flows which race down the sides of the volcano. Other times, instead of an explosion, sticky lava oozes out of a volcano and piles up around the summit. Pyroclastic flows can then form by parts of the lava collapsing. Although pyroclastic flows normally move down valleys, extremely hot, fast-moving, billowing clouds form above them, which can spill out of valleys. This means that even people on high ground are not safe. Pyroclastic flows normally travel to distances of 5 to 10 kilometres from the volcano summit, but in the biggest eruptions may reach much more than 20 kilometres. Volcanoes that haven't erupted for many decades or even centuries may appear peaceful, but when they awaken, the eruptions are often very large and explosive. Scientists can detect that a volcano is reawakening and are able to provide some warning or advice to evacuate, which is the only protection from pyroclastic flows.
Some of you may have recognised the voice of Professor Ian Stewart from Plymouth University, who was the narrator there. He's commonly been on the BBC on science TV programmes. So that was pyroclastic flows, and clearly you don't want to be around when those happen. There's another problem I'd like to highlight with eruptions. There's a French West Indian island called Guadeloupe in 1976, and that's got a volcano that's called the Soufriere. And in 1976, it started to show signs of possible eruption. Now, in actual fact, nothing actually really happened. There were a few small explosions and some earthquakes. Nothing really much happened. But this, what we call volcanic unrest, these small signs, went on for about 6 months. And there was an enormous row between French scientists. On the right, there's somebody called Haroun Tazieff, and on the left is Claude Alleg. And they totally disagreed. One said that the government should evacuate everybody, and that's what they did. And the other said it was a waste of time. And so we get this problem of false alarms and communication. So there was this big public row. And again, it was another pivotal moment in the science because people didn't want this kind of public debate and disagreement between scientists to happen again. And so what happened was they evacuated about 70,000 people from a town called Basse-Terre for 3 months. They put them in temporary camps, uncomfortable conditions, and then eventually they returned to the town. But that 3 or 4 months, of course, of being evacuated and their lives being disrupted was enormously stressful. Nobody died, but it did then seed a lot of distrust in scientists. And if you go, my colleagues from France who go on the island, and even nowadays, many people still don't trust the scientists and the government because of this episode. So this is another difficulty, that volcanoes will often show signs that they're going to erupt, and they don't. And this can lead to what's called false alarms. You evacuate everybody and nothing happens. Now I'd like to go on to another case which illustrates the terrible tragedy, one of the biggest of the last century. It's the Lahar at Almero in Colombia in 1985. It's a town which is about 45 kilometers from the volcano, Nevados del Ruiz. And this volcano has got a glacier on it, an ice cap. And when the eruption started, you got pyroclastic flows like you saw in the film, but they landed on the ice, and because of hundreds of degrees centigrade, they made the ice melt, and that created an enormous flood which went down the valleys of the volcano and gathered trees and rocks and stuff, and then flooded into the town. And 23,000 people were killed. And again, this was a communication issue. There was not, the scientists realized that there was a problem, but there wasn't the communication mechanisms or structure to give warnings to the people in the town. And again, for the Colombians, it was a huge tragedy, and they were determined not to do anything, have that happen again. And in fact, Colombia is one of the world's best monitored countries in terms of volcanoes. The scientists there are excellent. And since then, they've had many eruptions, but very few deaths. And it was really the response to this tragedy. Okay, so what is a lahar? Well, again, I'm going to ask Ian Stewart to explain that to you.
A major danger on many volcanoes comes from floods of water mixed with volcanic debris. These floods are called lahars. Lahars are more destructive than a normal flood because they contain large amounts of rock, ash, mud and debris. Boulders swept along by the lahar can sometimes be the size of a car. They can form very quickly and flow down the volcano into the surrounding valleys, often at high speeds. Several lahars often occur in quick succession. Lahars are a major cause of death in volcanic eruptions. They can travel great distances, many kilometres, or even many tens of kilometres, so communities far from the volcano can still be in great danger. There are many causes of lahars. A very common cause is if there's heavy rain. An eruption can cover the sides of a volcano with loose rocks and ash. Vegetation and soil, which normally absorbs the rain and prevents floods, can be destroyed by the eruption, adding to the problem. When it rains heavily, rock, ash and debris are easily swept into the water, forming lahars. The rocks and debris give the lahar extra destructive energy, and often the flows move much faster than someone can run. Some volcanoes are covered in glaciers and ice or snow. Eruptions of hot rocks can melt the ice or snow rapidly to form bursts of huge volumes of water that form lahars. Lahars can occur at any time during a volcanic eruption, but they can also happen many years afterwards. Fortunately, there can be warnings given about lahars. If heavy rain is forecast, then the chances of a lahar increases. For those places threatened, evacuation is the only option. If there's not enough time to evacuate, then people can protect themselves by immediately leaving valleys and going to high ground. Hiding in buildings is not safe, as large lahars can destroy buildings or flow into them. But the upper floors of a strong building may offer some protection if there's no alternative.
Okay, just to say that hopefully gives you an idea of what a lahar is, which is because the eruptions destroyed the vegetation and put a lot of debris on the volcano. And when it rains hard, you can get these terrible floods full of rock. And also when there's a glacier. These films, by the way, you can download for free. That you can get them on the internet, on Vimeo. And they're really designed to help communities understand the hazards and risks that they face. And we've now got these films in 6 different languages. Okay, so let's move to another case. This is, in some ways, a better story than the previous ones, in that we now move to 2010 and the eruption of the volcano Merapi in November 2010. There were 350 people killed, and that's, of course, a tragedy, but it could have been a lot worse, and it was because the scientists were monitoring, the Indonesian and US scientists were monitoring the volcano very well, that they decided that they would evacuate about 400,000 people, and they did that evacuation over several months. And it was good that they did that because they'd seen that the pyroclastic flows from the volcano could typically, in previous eruptions, had gone about 10 kilometres, but the volcano was behaving in a very unusual way, and their interpretation was that they were going to get a very big, much bigger eruption. And so, in fact, you can see that grey area in the valley there, that is the pyroclastic flow where it went down a valley, and it, in fact, went 20 kilometres and went through quite a few villages. And the estimate is that if they had not evacuated, the death toll would have been about 15 or 20,000 people. In these situations, you're always going to get a few people who stay behind for whatever reason, don't listen to advice, and of course that results in the terrible that 350 people were killed. But it's sort of in this sort of situation almost inevitable, and the result, I think, of this was a success in the sense that probably 15 or 20,000 people were saved. And that's just some pictures of from this. I went out there to get involved in the study. That's one of the villages on the up top left, where there were a few people who'd stayed behind. It's quite socially. It's quite interesting that actually it tended to be the men and the young men who was if you like, adolescent boys who were killed preferentially because the family would be evacuated, the sort of young children and the old people and the wives and so forth. But the men felt it was important to go back to their houses to see if they could rescue other goods or look after their livestock. And so some of those did go back and were tragically killed. You can see here, sort of rather unexpected, this is a dam which is to prevent floods into this village, but this dam actually caused more destruction. So you can do one thing to sort of save yourself from floods, but what happened was the pyroclastic flow hit the dam and went sideways into the village. And it was only because the dam was there. So you can sort of do one thing and there's an unintended consequence. There were lahars, and again you can see a lot of debris there. Those are from the lahars, and then you can see the evacuation camps that the Indonesian government had to put up. So this is about 2 or 3 months afterwards. There were still 20,000 people evacuated in camps. So going on to another case, which again, where we get some politics coming in. It's an intriguing one. There's a volcano called Galeres in southern Colombia, quite close to the Ecuador border. And it's got a big city called Pasto of about 400,000 people. And over the last 10 or 15 years, the volcano has been having lots of little eruptions. And some of them are a little bit bigger, they're not very big, but the Colombian government decided on a policy which is very controversial of relocation. And if you look at where Pasto is on the map, you'll see that there's a series of small villages which were populated by indigenous people. And the government decided that they would not just evacuate those villages, but they would basically depopulate them. They would relocate those people to other parts of Colombia. And as you can see on the bottom right, or the two pictures of the local people, they didn't think this was a very good idea at all. And they participated in town meetings where they were saying, well, we've lived here hundreds of years and not even a dog has been hurt. And we don't think, we think we know the volcano. And in a sense, they were right, and they rebelled and they refused to be evacuated. And eventually, after several years, actually, the Colombian government sort of decided that they wouldn't go ahead with a relocation. But that's another kind of, if you like, there was no tragedy here, but clearly a lot of concern and worry by the local people that they were going to be asked to leave their villages. So we now go on to perhaps the most contemporary big volcanic event, which was Krakatoa in December 2018. I think probably most of you in this audience would have seen that. And of course, again, another tragedy because there were lots of tsunamis. I just want to show you what some of the activity in December 2018. This is a volcano which you may know there was a huge eruption of Krakatoa in 1883, which formed a giant crater. And a new volcano started growing in that crater almost immediately. And it came, the crater was underwater, but the new volcano grew above water and formed a new island. And you can see some of the intense activities. So this was a new island building up in this ocean. And on the left-hand side, you can see a satellite image of the 21st of December. It's about a couple of kilometers across the volcano. We can see it from the sky. And the main thing about a volcano is it's a big, unstable object, and volcanoes are prone to having big landslides. So another hazard that volcanoes posed is simply being a big, unstable mountain. And it's a big, unstable mountain in the sea, and if it goes active, then that can be a trigger for instability. And that's basically what happened. And if we look at the before on the left and the after, you can see that big cone, that bay is about probably about 700 or 800 meters wide. The volcano has disappeared because it slid into the sea and pushed the sea away, and that was the cause of the tsunami. And the reason the tsunami is, of course, people can get caught in the tsunami, but it's very like lahars in some ways. The tsunami wave comes inland, and you've probably all seen films on the telly of this, it grabs almost anything in its way, buildings, cars, bits of wood, anything, and then the water flows back with all this debris, and once it's gathered all this debris, it's a bit like a lahar. It's very destructive. And that's what happened in Krakatoa. There was no tsunami warning system in operation by the Indonesian government at that time. They did have one, but it wasn't working. And so if that had been working, then the coastal communities would have had probably maybe 20 minutes, half an hour warning to retreat and basically go uphill. So tragically there, again, you can see that it's a human. Often disasters are caused by humans, not by the volcano in a sense. It's the fact they didn't have an adequate, an operational early warning. So I'm now going to go to my favourite volcano, which is in the Caribbean, one I've done an awful lot of work on over the years and been to many times. It's called Montserrat. It's a British dependent territory. It sits quite close, you can see on the map, quite close to Antigua. It's a mountainous island with a sizable volcano in the southern part. And before the eruption that started in 1995, it was a lovely Caribbean island with about 12,000 people living on it. It had never had an historic eruption. We know the last eruption must have been in the 16th or 15th century. So nobody had any experience of volcanoes. But the volcano began, and you can see that it's got all this grey material. This is taken I took in 1997. That grey mound is the lava flow, and that delta of grey stuff is basically the pyroclastic flow fan. And there was a sort of a bit of a joke. This is the first time since probably the beginning of the 20th century that the British Empire had grown by about a square kilometre because of this new land that was caused by the pyroclastic flows going into the sea. Pyroclastic flows were the danger. So the net result of the eruption was that the southern half of the island had to be evacuated. The town of Plymouth was destroyed, and those grey on the maps are where the pyroclastic flows that you saw in the film have gone down valleys. So you can see that basically the southern half of the island was really too dangerous for anyone to live. And so it was an enormous tragedy in a social particularly in a social sense. The population reduced from 12,000 to 4,000, not because anybody died, but because the island was too small to hold that population. They didn't have the facilities. So many people came to Canada, United States, Britain, or all around other Caribbean islands, and they had to basically leave. So there was an enormous sort of evacuation of the people of the island. Also, there were some people killed. Again, a similar problem that although the area was officially evacuated, some of the best farmland in the island was on the north side of the volcano. And you can see on the map on the top left where the pyroclastic flow of the 25th of June 1997 went. You can see the size of boulders that pyroclastic flow took down the valley. And then you can see the cloud of hot ash over houses formed by the pyroclastic flow. It was moving so fast it went 100 meters uphill. Now, unfortunately, a number of farmers had gone back to again tend their crops, look after their livestock and so forth. They were living in very primitive shelters at the time, and so it wasn't really a surprise that some people would want to come back and take the risk. So there were some tragedies, but again, rather like Merapi, I think the overall story is that a lot of people's lives were saved by the evacuation and the monitoring. This is some pictures of Montserrat. On the top left is the beautiful old town of Plymouth, unfortunately completely buried under pyroclastic flows. On the bottom left is the hospital which the British government spent something like, a lot of money on. Anyway, that was the new hospital, which was destroyed, even though there was some warnings prior to the eruption that this Plymouth was very vulnerable. And so the net result was 9,000 people relocated. There were 20 deaths. The estimate, this is back in 2003, is that there was about $1 billion of losses, economic losses. And ever since then, the island hasn't been self-sufficient, unfortunately. And so it's costing the UK taxpayers and overseas dependent territory, it's costing us about £30 million per year to keep the island going. So it's cost the UK government a significant amount, and those costs are still being accrued. Just a story of my own that was while I spent part of the time in the first 3 years of the crisis as the director of the Volcano Observatory. And this is sort of a bit of a cautionary tale. On the the two photographs are of the southwest side of the volcano, and you might, if your eyesight's good, see somewhere called Galway's Estate. And these pictures are looking at the volcano from about there. And the picture on the left, you can't really see this, but there's actually a picture of an earthquake. There was an earthquake going on, and lots of that wall was sliding away, and lots of the ground was cracking up on this side of the volcano, and we were very worried that there would be a very dramatic, violent eruption. This is October 1996, and people were evacuated from these areas to avoid this problem. But actually nothing very much happened for quite a long time. The wall was clearly unstable, and clearly there was potential for a big event. But of course, nothing happened, and the local people would be sort of talking to you in the street and saying, yes, you scientists don't know what you're doing, nothing will happen. So 14 months later, I was chief scientist of the director of the observatory over the Christmas period, and I went up to that same place, 21st December 1997, and we looked over, and we can't see that wall anymore because grey lava and stuff, volcanic debris, has buried the wall. So we still thought this was pretty dangerous. And on Christmas Day, we were having a party in the observatory when the seismometers started to go, and they really started to go, and we realized something was amiss. And then the very next morning after Christmas, we went out and we found basically total destruction of that side of the volcano. What you're looking at, perhaps I can just draw your attention to the bottom right picture. You can see that's an area where the villages which are there are completely disappeared. And that's because there was a pyroclastic flow that went all around this area at 300 kilometers per hour and just wiped absolutely everything out. If anybody had been there, they would have not survived. So that was what we call the Boxing Day event, and it was very dramatic. And so what we'd been fearing did actually happen, but it happened 14 months later. Okay. Just to show you living with how the Montserratians lived with a volcano, this is what we call the zone. It's a small island, and there's a quote here that a famous quote that somebody on the island said, "This island is exactly the wrong size for an eruption." And the reason they said that was that if it was a much bigger island, it would have been very easy to have accommodated the people who were evacuated and put them somewhere else on a big island. If it was a smaller island, then you would have had no choice but to totally evacuate it. But the Montserratians are pretty resilient people, and they wanted to basically carry on living in the top third. And you can see some of the ash that was produced, which made life unpleasant. You can see one very creative guy put his house on a truck and took it to the north. And then you can see a great picture for these sorts of events. There's a big explosion going on, and there's a guy who's completely ignoring it because by this time, 2 years into the eruption, they were used to explosions. They wanted to get on with their life. And I remember going to the cricket ground on the island to watch a cricket match, and there were some spectacular explosions going on in the volcano, and I was with my scientist friends. We were all watching the volcano, and all the locals were ignoring it and getting on with their cricket game because they'd got used to it. So it's amazing how resilient people can be to an event of that kind. And then later in the eruption, we basically made it a much simpler management map. You can see the red area, nobody could be there, and there's the northern zone where people could carry on with their lives, and the Montserratian people could build up the island again. Okay, just a little bit about some of the work that we did with the UK government and the Montserratian government and crisis management. We formed a risk assessment panel, which I chaired for many years, and its job was to assess the hazards and risks at the volcano every 6 months. use observations and models, and something I'll tell you a little bit more about, expert elicitation. Our output were reports and risk charts and discourse discussions with people like the governor and the Prime Minister of Montserrat and UK ministers back in the Foreign Office. And we reported the risk in terms of chief medical officer scale and analogies similar to the public. And so we were basically the committee or panel which gave the advice. And the eruption, I should say, went on for 15 years. So it didn't stop in 1996-7. It went on till 2010. So it was a long-running emergency. And we developed some fairly novel methods, which is essentially something called expert elicitation, and it's quite entertaining to talk about it, but I think it's got a serious side. So what you're interested in, and if you look at the words, we've got this question, what's the chance of a major explosion in the 6 months? What's the chance that a village 6 kilometres northwest of the volcano will be affected by pyroclastic flow? So these are the practical things that governors and chief ministers and services want, protection services want to know. Where are the dangerous places? And so what we did was we had a panel with our colleagues from the University of the West Indies, and we did something called expert elicitation. And I'm going to, perhaps not to look at the slide for a moment, and I'll just talk you through this. If we have a typical response, we have a committee, we get a committee of experts, and they all say their things, and they try to come to some sort of view. But the truth is that most people are very varied in how expert they are. And if you're trying to forecast the future, then there's a lot of uncertainty. And we wanted to capture that in a methodology. So what we did was we calibrated the people on our committee, including me. And so how good an expert were you? And this is an example. Let's just go back. If you look at I haven't got a pointer, unfortunately, but look at expert 1, and the little arrow is meant to be the right answer. And I'll give you an illustration. Let me ask you the question. How many litres of red wine did the French drink in 2018? Okay, that's your question. And some of you may be experts because you go on holiday in France and drink a lot of red wine. Some might be great experts because you are a wine merchant and you know all about the statistics of French wine and so forth. So it's a daft question, but it illustrates the sort of questions we asked our experts to see if they were any good or not. And so a good expert, the arrow is the real answer. An expert 1 gets it spot on, but more important, they've got a spread. They're asked to say what's the most it could be and what's the least it could be. So that person got it right. Expert 2 got it right. That expert got but they've got a very large spread. So it's like saying how much red wine did the French drink, and you say well, anything from 10 litres to a trillion litres, and you know that the right answer must be somewhere, but your guess isn't very informative. That's not a very helpful guess. But if you're very precise, you say it's exactly 7,342,685 litres with very little spread, and you get it wrong in a hazard situation, that could be a disaster because you've made the wrong, you're too confident in your expertise. And then there's somebody who doesn't even get the right answer, and they're obviously not so good. And you can plot, I won't say what these parameters are, but in the chart, these are parameters which basically say how expert people are, how much they know, and how good they are at judging uncertainty in any circumstance. And so the more to the right you are, the better you are. And the problem is that if you look at the numbers, each number is an expert. Experts 1, 5, and 9 are pretty good, and expert 18 is not very good at all. But the numbers are the rankings of how, if you like, their esteem. If they're an esteemed professor, then, or they might be a young student. And you can see that number 1 is indeed the top expert and does very well. Look at number 2. That's your opinionated person on a committee who thinks they know everything. and they don't know nearly as much as they think they do. And so what we do is we use that to run our risk assessment. We had a real situation in 2003 when the volcano was very dangerous. We were worried about the pyroclastic flow getting to a particular village. On the left, there's a map showing you where that village is. There were several hundred people there, and on the basis of our estimates, we evacuated the village. Now, this is I'm afraid, a bit technical on the left. It's what insurance people use. It's the probability of a number of people being killed in a certain number of period against the number of fatalities. And so what you do is a risk curve. If you're on a risk curve, the red one, basically if you keep the people in the village, they're very vulnerable, the risk is very high, and you've got a 1 in 10 chance of a really a tragic situation. If you evacuate the people out of the village, then you get the next grey curve, and then it goes to 1 in 100, and then if you go down to the other grey curve, it goes to 1 in 1,000, then the risk is okay. And the blue and the green are the risks of being, if you live in the Caribbean, of being a fatality due to an earthquake or a hurricane. And so if we could reduce, so we don't want to take people too far away, because they've got to get on with their lives. So what we did was we got them the evacuation zones so that the risk reduced to the same risk that they faced as a consequence of living in the Caribbean from hurricanes. So that's how we use that. And what happened? Well, when we did the risk assessment, this is the volcano in July 2003, we thought the most probable thing was all that stuff, just like in Krakatoa, would slide into the ocean to the east. And that's what happened. The whole mountain disappeared into the ocean. And we also got a tsunami on that day. So the risk was reduced. There wasn't a dangerous mountain there anymore, so the people could go back to their homes. Okay, I'm going to go through this last one fairly speedily. It's the last case I'm going to deal with. It's probably the one a lot of people in this room might have been affected with, is the 2010 eruption of a volcano in Iceland in the summer 2010 when, as I think everyone knows, the airlines had to be shut down over Europe. I was involved with the National Committee with people from all sorts of different organisations in order to give advice during that period. And Iceland, just to say, that I think the headline figure is here, the eruption, there's an eruption in Iceland every 50 years, and this one wasn't a particularly big eruption. On the bottom, on the right-hand side, you see the eruption which caused the problems. It's quite a small volcano. It hadn't erupted since 1821, so nobody thought it was very likely to erupt. In fact, there's another volcano in Iceland called Katla that people think much more likely, they thought was much more likely to erupt. So this little volcano erupted in March 2010, tells you a little bit of the history, and it's those weak explosive eruptions on the right in April and May that stopped all the aircraft in Europe. And so why did that happen? Well, we got a combination of a small volcano which erupted in a glacier, and the explosions broke up the lava into lots of tiny dust which could be transported a long way. And unusually, the wind was blowing to the south. This stuff usually goes over Scandinavia and doesn't cause us any problems, but we were unlucky that the wind was blowing south. And so what happened, this is a satellite image of this eruption, and the reds and greens and so forth at different times are showing you the spreading of this ash cloud over. So wherever you see greens and red, there's a lot of ash in the air, and you definitely can't fly through it. And I think the main thing I want to just emphasize is just how quickly this stuff spreads up over the entire part of Europe. Very hard to predict, and also quite complicated patterns. That makes it hard to predict. So people couldn't really, Europe is the busiest air traffic in the world pretty well, and you couldn't really, you really couldn't fly any aircraft if people thought this ash was going to take. So let's have a look at a movie from some of my colleagues at Bristol who've been running computer models of the spreading of the ash. So here's our eruption, and this is their computer model showing you the ash. This is probably about 12 hours of activity, something like that. The ash cloud spreading in a complicated way over Europe. That's really why the planes had to stop. The problem was that if you get some of this ash in an engine, the engines are known to stop. And there's a famous British Airways flight going over Indonesia where all 4 engines stopped. And there was almost a tragedy, but one of the engines, when they got to 5,000 feet and thought that was it, one of the engines stopped, and a British Airways pilot managed to land the aircraft. So ever since then, people have said, let's just avoid this stuff. We won't fly through it at all. So when the ash came over Europe, there was really wasn't an option. Just to show you that the Met Office, some of the work the Met Office do at Chilbolton, and just to show you just north of Southampton, this is something called LiDAR. Basically, it's a way of imaging the dust in the atmosphere, and this is with time. If you look at that green squiggle, between the Earth's surface and 3 kilometres, there was an enormous amount. Wherever you see it green, there was an enormous amount of ultra-fine dust over southern Britain. So it just shows you how far this stuff got. And this is just something you can download from the internet. It's a great movie. It's the 24 hours of flights around the world in 1 minute. And I've just got a snapshot. Unfortunately, it's not. It's when when there's no flights over Europe because it's the middle of the night. But you can just see each yellow dot is an active flight. And you can watch these yellow dots go all around the world and realise just what an enormous issue it is. You can even see the Mexican border over the United States from this. But it's when you've got that enormous crowding and the possibility of a tragedy from ash injection that you'll go. So what happened? Grounded aircraft for 6 days, probably $20 million a day, those few days, $1 billion. It's probably it's significant political fallout and travel disruption insurance claims. So huge amount of damage. I think I'll miss that one out. Oh, sorry, I think I'll keep this one in just to say that now the world has 9 new areas where there's meteorological officers in each of these areas, which their job is to forecast where volcanic ash. Remember I said there were 50 eruptions a year, so this is happening all the time. So the Met Office controls what we call the London VAC. Toulouse controls the a very big area. And these people's job is to do those computer models and tell you where the ash is going and stop either make the aircraft avoid the ash or whatever. So just to say, last couple of slides now, it is a very interesting episode because environmental protocols and standards, which have been going on for 20 years, which is basically avoid the ash, were changed overnight. And they were changed overnight by people like Willie Walsh and so forth, who were saying, we're coming in even if there's ash. And our engineers say it's okay. And so there were 25 flights coming in over that weekend when they shut down. And I think it was Lord Adonis and his group decided they'd open the skies again. But it was a very hurried decision, and basically an environmental standard was essentially torn apart overnight. It challenged international practice. As I say, operational responses changed in a weekend. And there was some sort of, it's still really very unclear. There was a lack of transparency. Basically, the engine manufacturers looked at what happens when very fine dust gets in their engine, and they concluded it was okay to fly in small amounts of ash. Right? The rule was you didn't fly in any ash at all. And they never really let their data out. They still haven't, because if Pratt & Whitney or Rolls-Royce say, well, my engine's not so good for ash, and publish that data, and their engine isn't quite as good as Pratt & Whitney or vice versa, then that's got huge commercial implications. So they never really publish the data on which the basis of opening the skies again. There were some lessons learned. It was complex decision-making, decision primarily derived by a computer model of the kind this is the Met Office model that's just called NAME, but it's a computer model to say where the ash is going. There are lots of different organisations, UK Government Department for Transport. Chris Grayling wasn't the minister at that time, so thank goodness. The CEA and European partners. There was obviously lots of governments around the world, and these acronyms you don't really need to know, except that lots of different people have to get involved: engine manufacturers, airlines, transport ministers, civil servants, scientists like myself, passengers, insurance industry, and an awful lot of actors are involved. And Britain didn't have volcanoes on their national risk register. Of course, everybody knows Britain doesn't have volcanoes, but it's now, as a consequence of this, it's now on our national risk register, which is updated every year, and there's now a system which in 2011 actually worked much better when there was another small eruption in Iceland. So hopefully this sort of tour of different volcanic emergencies has given you some flavour of what volcanoes can do, and I'm happy to take some questions. Thank you.